Hi and welcome back to Power Electronics Lectures. In this lecture, we will talk about the multiphase diode rectifiers. Multiphase rectifiers use multiphase power supplies in order to supply higher power applications than single-phase power supplies can do. A multiphase supply can be used by a rectifier to supply a constant DC voltage, which can easily be filtered, producing at the end a less ripple output compared to single-phase rectifiers. Let's have a look at this circuit, which is a diode rectifier, three-phase half-wave rectifier. Here we have a three-phase input. Let's say this is VA and VB, VC. We know that the three-phase waveform is a sine wave input with different three-phase power supplies, and each one of these supplies are shifted by 120 degrees. And if we add these waveform together, we will get zero voltage at the end. So here we have, let's say this is waveform number A, VA. Let's say the blue one is VA. And then we have VB shifted by 120 degrees. And finally we have VC also shifted by 120 degrees. If we add these together, these three-phase waveform must give us 0 volt. Look at the voltage potential here on this diode, diode number 1, D1. You'll find that the voltage applied on this diode is the difference between this point here and this point. When the voltage applied on this diode from here to here is larger than any one of these diodes, so definitely the diode 1 will be on and other diodes, diode 2 and diode 3, will be off. So let's have a look at this waveform. When VA, the blue one here, is larger than VB and VC, then at this moment VA is the winner and diode 1 will be on, right? When diode 1 is on, this means this is short circuit here and this is open circuit, and the voltage across the load, let's say this is a resistive load here, so the voltage across the load V out is equal to how much? The difference between this point and this point, which is VA. So this portion here, it will be the output, V out, which is coming from VA voltage, VA phase. Now, at this point, when VA became less than VB, so who is the winner here? VB. VB is larger than VA and VC, and at this point, diode 1 will be off. This will be open circuit, and diode 2 will be on, will be conducting. Okay, so at this point, diode 2 will be on, and this portion will come to the output. Same thing will happen when phase C became larger than other phases. So both diode 2 and diode 1 will be off, be open circuit, and diode 3 will be on, means conducting. And here, this portion from VC will go to the output. So this is diode 3 is on. Don't forget that this is a half wave rectifier. So diode 1, diode 2, and diode 3 is applied only applied on the positive half cycle of the input. Now when diode 1 is conducting, so the voltage across diode 1 is how much? Is 0, because diode 1 is short circuit. Okay, so if you try to find the voltage across diode 1 here, you'll find that diode 1 has 0 voltage. This is the voltage on diode 1. Now from this period to this period, during this period, from this point to this point, how much is the voltage on diode 1? You'll find that here diode 2 is on, means conducting, and diode 1 is open circuit. So the voltage across diode 1 is the voltage from here to here, from this point to this point, right? And this point actually is connected to what? To VB. This point is connected to VA. So the voltage across diode 1 is VA minus VB, which is VAB. This is the line voltage, VAB. So it will be something like this. And now, in this period, from this point to this point, when diode 3 is conducting, is on, so this will be short circuit, this will be open circuit, so the voltage across diode 1 is VAC. And this is again the line voltage. And so on. Now this is the full period completed, then after that everything will be repeated. So the period from here to here, the full period from here to here. T. Now the full period for this output looks like this. So this is the full period, which is T, right? And this is V out. This is VA, VB, and VC. And it seems that these voltages here, these three voltages are similar. So if we take the average for this one, as if we take the average for the whole period. So we can easily say that this voltage here, the average for this portion, is exactly the average for the full period, no problems. So we can take the average for this portion, which is how much? The limits for this portion. Now this period is how much? T over 3, and this is T over 3, and this is T over 3. And this absolute will be how much? Minus T over 6 to T over 6, and this is cosine 2 pi T over T. Why cosine? Because we need to be benefit from the limits here. If we say that this is sine, so we don't know exactly when this sine starts or when it ends, right? But if we take the axis from here, so exactly we know that this is 1 or the maximum, okay? And here minus T over 6 to T over 6. If you know the limits, so make it sine, no problems. If you don't know the limits, so define the limits by what? by taking the axis at the middle of the top of this cosine wave. Okay, so we can say that the average value here, now V out is V maximum times cosine 2 pi t over t, and the average value for the output is how much? Integration from minus t over 6 to t over 6 for V maximum cosine 2 pi t over t dt. And in order to find the average, we have to divide by the period, which is t over 3. Now the integration for cosine is sine, so this will be sine 2 pi t over t capital divided by 2 pi t capital, and here we have t and 3 as well, and we have V maximum. All these are constant, and this from minus t over 6 to t over 6. T with t, and this will be 3V maximum over 2 pi times sine pi over 3, just substitute by this value here, minus sine minus pi over 3. Finally, this will be 3V maximum over 2 pi times the root square of 3 over 2 minus the root square of 3 over 2, and this will be how much? At the end, the average for this is 3 times the root square of 3 V maximum over 2 pi. And this is the average for the output voltage of three-phase half-wave rectifier. Let's have a look at the three-phase full-wave rectifier. Things here are a bit complicated compared to the three-phase half-wave rectifier. Let's look at these values here. Now here we have VA and VB, and here we have VC. Now the waveform that's coming back from the load is coming back to 3 diodes. Okay, so this is one difference, number one. And if you try to look at these values here we have VA, VB, okay, and we have VC. And here we have also two nodes. Node number one, the terminal of the load, and here we have node number two, the other terminal of the load. Of course, this is the same node here. When VA is larger than VB and VC, what happens? Look at this waveform here, VA, the blue one. Here, this VA is larger than the green and larger than the orange one. So VA is larger than VB and VC. At this moment, diode 1 is on. Okay, diode 1 is on. No doubt about this. So the waveform will go, and this one will be open circuit will be off, okay, and the voltage will go to the load and come back to the negative side, to these three diodes, okay. Now when the waveform is coming back here, we need to look at the smallest voltage, okay, the minimum value. Now here we have the orange is how much is VC, right? So VC is smaller than VA and VB. So here diode 6 will be on, and diode 4, diode 2 will be off, and the waveform will become like this, okay. So here diode 6 is on and diode 1 is on, and the output voltage is equal to how much? V out, the difference, VA minus VC. It will be VAC. In this cycle, when VA again is larger than VB and VC, so that one will be on, this will be on, and this will be off. But if you look at this moment here, you'll find that VB became smaller than VC and VA, okay. VB here, so diode 4 will be conducting, and diode 6, diode 2 will be off, and then here the waveform is coming like this. The voltage is coming from through diode 1 to the load, then back to diode 4. So the voltage will be how much? VAB. And which one of these diode will be on? Diode 1 is on, and diode 4 is on. Now, here at this moment, VC is larger than VA and VB. So VC, which is diode 5, the positive part, diode 5 is conducting here, okay, and then other diodes will be off, so diode 5 is on at this moment. Why? Because VC positive part is connecting to diode 5. So the current is coming through this diode, going to the load and coming back. Now, if you remember the previous negative voltage is conducting with diode 4, so diode 4 is what? Is on, and again here diode 4 from here to here is smaller than other voltages, so it will keep going to diode 4 like this. So here also diode 4 is on, but from here to here you'll find that the blue voltage, which is A, is smaller than other voltages, so diode 2 will be on. Okay, and so on and so forth. So for this cycle here, diode 5 is conducting, the current is going here, and diode 2 then is conducting and going in this way. Now, if you look at this portion here, this VB is larger than others, so VB is what? This voltage, so diode 3 is on. The current is flowing this way and will go. Diode 2 is on, so it will go like this. So here diode 2 is on. So this is the fifth case. The last case, which is the sixth one, number 6. So diode 3 is on, and here is VC is smaller than other voltages, so diode 6 is on. So it will go through this. Diode 6 is on, and then diode 1, diode 6, diode 1, diode 4, diode 4, diode 5, diode 4, diode 4, diode 2, 2, 3, 3, 6, and so on and so forth. Okay, and the voltage is here. The output voltage is how much? This is VAC, VAB, and here VCB here, and then VCA, and here VBA, and finally VBC. Okay, so the voltage is like this. This voltage, the output will be this output. And as you can see, the ripple here is much smaller than the ripple in the single phase or in the 3-phase half-wave rectifier, because here we have 6 waveforms collaborating in order to generate one DC output, right? And the output will be something like this. This is the output voltage. Okay, VAC, VAB, VCB, VCA, VBA, and VBC. That's everything for today's lecture. Next time we'll talk about the rectifiers with the effect of line impedance or with the effect of impedance in general, and we'll see how such impedance can affect the behavior of the output voltage, or even not the output voltage, and also the behavior of the input voltage and how this can make distortion for the input and the output. See you next time.